Okay, so we're going to move into a couple sections where we may have to go back in the future and do some additional work so that we can get some additional stabilization done on some of these emergency sites that we have currently got completed and have done some temporary measures like seeding and mulching and try to get some vegetation growing. But there's something that we need to do after the emergency and go back and monitor these sites and see if there's some additional items that we might want to look at adding to those. So one of the topics we're going to discuss is the bioengineering techniques, which is more vegetative type techniques that we might be able to do to the site after that initial channel reconstruction. So here are some of the bioengineering techniques that this section will take a look at. That's live willow staking, riprap joint planting, that's planting live stakes and riprap, coconut fiber roll usage, live fascines, brush mattresses, brush layering, some vegetative geogrid, and a live crib wall. A lot of these are used together sometimes to meet different needs on that after that reconstruction. So live willow stakes basically are live stakes, cuttings, basically 2 feet long, sometimes a little shorter, something that's rugged enough that we can drive into the bank by using a mallet. Or if we have to, we can use a smaller material, single stakes, and take a pry bar to make a pilot hole and just basically push them into the bank. You can see the photo on the right with the live stake placement. Arrow is pointing. They've basically driven those live stakes into wherever they could get them into that bank so that those cuttings will root themselves and begin to establish an vegetation that will help support that embankment. Riprap joint plantings, basically doing the same thing, but you're trying to get it in between the rocks. A lot of the permit stuff that we end up doing, or the permit applications that we end up doing, those riprap walls that we have done in the past, generally the environmentalists like to see us putting something in there that's going to grow and help produce shade or shading of some of those stream channels. So in this case here, we can use that, get material in between the rocks. Now, the only challenge to this is if you end up with a design that has you using geotextile underneath rocks, it's more difficult to get those plantings in, because then you have to actually poke a hole through the geotextile so that you can get that live stake in there. But generally speaking, we're generally changing our designs now so that we don't have to rock that entire embankment all the way to the top, but maybe only do some toe protection and then do a bioengineering on top of that at a certain stream event depth. Coconut fiber logs can be used too to help stabilize the toe of the stream so that we can get vegetation established above it. It's just another method of giving us that extra protection for a little while until we can get our bioengineering techniques above that elevation established. The only challenge I've seen with the coconut fiber logs is that they're sometimes difficult to get staked in good, and you still want to try to get those embedded into the stream bed just a little bit so that you get some anchorage. They've driven live stakes into that core log, but you notice they have to actually stake them on the outsides to get them to stay into place. So All depending on what your bank full flow is where you want to get those core logs put in at the elevation. Live fascine placement. Basically, this is taking what we called willow waddles, and this is what I am calling a willow waddle. It's basically a bundle of small willow branches wrapped together with either baling twine or some type of twine to make a bundle, and then you dig a trench in that floodplain area just above, right at bank full or in that floodplain area, and you get the trench dug in there. You lay these fascines in that trench. You stake them in certain places to help hold them down, and then you just basically backfill the whole trench. And these fascines will germinate and send roots down into this area and send up massive vegetation above them. They work really well. They're very, very rugged. Once they're established, they act as a good erosion control on those embankments. Brush mattressing, it's a method that's been around for quite a while. And you notice on this stream shot to the right, they've got some type of riprap reinforcement here at the toe, probably up to about what bank full flow is. And then they're protecting that slope above that with this brush so that they're laying down those waddles or fascines at the toe, and then they're laying brush all over. And they take a wire and stakes and they kind of wire that all together so it stays in place. And then they will probably cover this area with a little bit of soil so that they can get ground contact on that so that they will start to root. This is just the slide to the left. It's just a typical detail of how that works. That's another bioengineering type technique. Brush layering is kind of the same thing as sticking in root fascines, but basically what we're doing is we're layering them up the bank in between layers of soil. Here they're using a combination of a core log plus the live fascines laid in there and then backfilled with soil over the top of all this so that it holds them in place. And then all this will root and grow up in a large vegetative mass. Vegetated geogrid. Geogrid's a material that you can see it here in the slide. It's this checkerboard looking material. This works similar to the brush layering because what we're doing here is we're building soil lifts with this geogrid to help hold the soil in place. And then in between every lift, we're laying vegetative fascines in there so that they actually root and start to grow. Again, you can notice that there is riprap at the toe here that was put in probably to a certain stream elevation, whether that was bank full or above, depends on the engineer's design. But beyond that, we can use a vegetative embankment, especially when you're dealing with such a high slope and steep embankment. So combinations of a number of different things used here in order to get that vegetation established. And there's the slide of it. Actually, this slide was one of the original slides that were shown earlier in the program where this stream had eroded up and underneath where the garage was. And I remember stating that that project there was going to take some more engineering and more thought on how to stabilize that rather than just an emergency situation. And this is what they came up to it. So they've got toe protection here to a certain elevation, whether that's bank full or a storm event above that depends on the designer. And then above that, they can use vegetation with the geogrid to a certain elevation. And once they got where they could slope it maybe to a 2-on-1 or 3-on-1, then it looks like they might have been able to just use grass seed or seeding. Crib walls, another method where you build an actual crib and you lay vegetation or willows or dogwood cuttings or any type of cuttings in there that grow in wet conditions and have them grow out between the logs. Generally speaking, these types of systems are probably used in a stream system that has lower velocities. Basically, you're going to want to get them towed into the stream bank just like you do with a riprap project. And then you're going to want to rock fill the base so that you can keep it all tied together. Hydraulic structures. We have a few slides of what we call hydraulic structures, which are structures that are made out of stone to try to assist the stream in stabilizing the stream bank. Just wanted to make a note that for future site mitigations is what these structures are generally used for, and there need to be some certain design criteria that you're going to want to meet for those structures, and it takes a little bit more time than just doing emergency work when you're trying to decide what to do and where to do and how to use these types of structures. So this generally isn't something we do during the emergency situation, but we're always making notes after the emergency occurs and we get that project done to get the stream back where we want it, the proper channel size. We may need to do future stabilization, so some of these structures can assist with that. We can make these structures out of rocks or logs. There's different names for them all, but there's barbs and riprap, and there's cross veins, and there's straight veins, and we have JHooks, and we can build step pools, and there's hardened riffles that can be used to help stabilize. Hardened riffles are used quite a bit to stabilize grade control. If you think you need to use any of these structures, make sure you get a hold of your local saltwater district to see if they can assist you, or the DEC office to assist you with some decisions that need to be made. Here's an example of some riprap that was put in because of the bank scour erosion that was done. You can notice that we don't need to be making sometimes perfect filled banks. We're trying to stabilize the toe at a certain elevation so that we don't get that landsliding occurring on that bank because it's so steep. Sometimes if you can get this type of protection done on these steep vertical banks, these banks will actually heal themselves up over time so that you don't have to be trying to fill in everything from the top of the riprap to the top of bank. This structure right here is what we're calling a stream barb. It's a triangular shaped area that's filled with rock, which is constructed. There's another one up here, and I believe there's another one up here. And basically what this is doing is it's actually taking the velocities or flows and it's moving it out away from the edge of the embankment here. Anytime a riprap project's installed without these structures, that flow always wants to flow right along the toe of this slope. And when we armor the bank and stop that erosion, then the stream is going to want to erode someplace else. And without these barbs, it actually will erode at the toe of this slope. So these barbs are taking that velocity and moving it back out to the center of the channel away from the toe of slope, creating a backwater area right in here. Very, very effective, but generally these definitely need to be engineered because you have to cut that perfect channel size perfect floodplain, perfect elevation on the height of the rock you want, and all that needs to be taken into consideration. So this slide here is showing us a picture of a cross vein, and basically a cross vein is a structure that goes all the way across the channel. And they're installed for head cut control or incision control, or trying to protect, in this case, the footer of a bridge structure or a culvert outlet possibly. These take quite a bit of engineering and design in order to determine the proper width the structure should be at bank full flow and the proper elevation, because you don't want to put these in and disconnect the stream from its floodplain. This structure here was designed as a two-step kind of cross vein because of the hydraulics that occur when these structures are put in. It changes the velocities within the channel in that section, and they always seem to want to dig a hole. So in order to keep the structures from collapsing on themselves, they are now coming up with a design that has a double step pool system to it, so that the energy is knocked out of that hydraulic jump before it gets all the way down to the end of the structure. You can notice that the rocks that are tying back into the bank there are no higher than bank full elevation, so that the stream can actually, during its flood stage, can go out and access the floodplain. Do you have any other comments, Mike, on these structures?
Yeah, and as you mentioned, these are very specific and need a lot of engineering. You know, that cross section of that structure should be matched to what the cross section of that stream should be. The steps that you see in that structure, you know, probably should be designed so to facilitate any kind of aquatic migration, if you want to look at that. And also, you know, I just, from a personal perspective, you know, want to add point of view that you always want to have a light finger when you're hardening that cross section of that stream, because it, you know, when you harden it, you really aren't considering any change in hydrology or any adjustment that stream might make. So you see a lot of these structures, as Jeff mentioned, near a bridge or near a structure that you want to facilitate transport of sediment through a reach or whatever. But again, if there's any change in hydrology or any changes in the watershed that might cause that stream to start to adjust, if it adjusts around this structure, then that structure is kind of obsolete. So again, you know, hardening cross sections and sections of stream with heavy rock should be done, you know, with care and a lot of consideration. So thanks, Jeff.
Thank you, Mike. Straight veins are basically a rock vein that is angled upstream to move that velocity back out away from the toe of the bank. So you can see this vein here. It's angled upstream on a certain degree from bank. That degree is figured out on each site differently depending on the meander bend. This one here, you can see how it's bringing the flow down. It's creating backwater in here. Using just these structures in this scenario has eliminated us having to riprap the entire embankment in between them. It's taken the velocities away and allowed these things to naturally stabilize with natural vegetation. You can see where the new thaw leg, or the actual velocity, is way out at the ends of these structures, and this is where the riffles and pools will be developed in the future. JHook is the same thing as a straight vein, but basically for fish habitat, they take it out a little farther into the channel and hook it and dead end it in this area here someplace. Probably, usually you want to dead end it at about bank full, but This is just basically trying to make a pocket here for fish habitat. You notice that the straight vein part is protecting this embankment from here all the way up, and now we can just stabilize this with vegetation. And we don't have to riprap the entire embankment. So that's sometimes the advantage to the straight veins and JHooks. Step pools are definitely installed for grade control. You can see how steep this particular scenario is. We've got a town road or a county highway or a state highway up here. We're attempting to try to keep this stream from digging any deeper, because the deeper this gets, the more embankment sloughing we get or erosion. And we're trying to protect some infrastructure up here. So in order to stop that head cutting on this stream, then this step pool system has to be reestablished. If you remember from the beginning of the program, we were dealing with two different types of stream scenarios: a step pool system and a pool riffle system. Step pool system being on a stream that's probably exceeding or somewhere around 4% or greater. And if we had a flood that came through and actually disturbed the natural step pool in it, we sometimes have to go back and reestablish that step pool system again in order to stabilize that embankment. So it's important to know what type of stream system you're working in. Those rock veins and barbs generally work in that riffle pool system. But when we get into having to do grade control in a very steep section of a stream, we're looking at more of these types of scenarios here. Hardened riffles. These work very well for grade control. In this slide here, you can see the hardened riffle that was installed in this area here. The reason it was installed was because once we took our data that we collected from the field, we noticed that our stream slope was probably getting above 2% or so, or at 2%, and we needed to do a project downstream of this, or we needed to do it through this reach, and so we needed to get some grade control in there so that we didn't create that darn head cut that we have to deal with. So these hardened riffles are installed when we have to do head cut control at the beginning and end of that construction. These work very well because they fit in with the stream itself. They create good fish habitat passage, and they just do an excellent job. I've used these more often, more so than cross veins and that sort of thing lately. Another example of a hardened riffle. We must be getting close to a structure down here near infrastructure or a culvert or a highway or bridge. You can see how this is all being used for grade control, set in at an elevation where we can reconnect this stream to the floodplain. This is probably the floodplain of this entire stream here. So it helps us control that depth of channel, and when we need it, when we're in a situation where the grades might be a little steeper than we like. This is the information contact slide, the last slide of the program, I believe. We can be reached at the following websites. For myself, Melissa Yerrick, she's our wetland program team leader. Mike Lovegreen, who's helped with this program, he's our stream team leader. Wendy Walsh is our coordinator. And there's contact information for the Tioga County Saltwater Conservation District if you need further information. The website is right there. So I just wanted to make mention that we'd like to acknowledge the following organizations and individuals for assisting us in putting together this and developing this program. so that we were able to share it with all you folks today. So appreciate all the hard work that went into this program from all of these individuals, and thank you very much.